Okay, let's get started then. And thank you very much, everyone, for attending. As Professor Dinçer mentioned, I'm going to talk about intelligent architecture for intelligent machines. And I think this is going to be a talk about questioning whether we're designing the right kind of systems going into the future, systems that are going to make decisions for our lives, systems that are going to take us to the space, systems that are going to solve problems like climate, and systems that are going to drive us around everywhere, and who knows what other things, systems that are going to make decisions for our medical health, systems that are going to understand the consequences of pandemics and try to fix them. And the question is, are we really designing the best architectures that can guide us into the future and be helpful for humanity? And I'm going to question the way we design our machines today. And I think I will start with something that's not controversial, let's say. Computing today is bottlenecked by data. We can generate much more data than we can process. And we can see this in applications that are exploding today. The machine learning revolution has been happening because we actually have a lot of data we can train models on. And we also have powerful processors to actually make sense out of that data. But this is not just in machine learning. All important workloads are data intensive. I'm going to give examples from genomics soon. And these workloads require rapid and efficient processing of large amounts of data. And we're doing much more sophisticated analyses on the data so that the data can be much more useful for us going into the future. And hopefully this is used for good purposes, of course, right? Technology is in general agnostic to morality, but hopefully my goal is really to enable some forward thinking so that we can actually do good things with the data for humanity. And on top of this, data is increasing. We can generate much more data than we can process today in many, many domains. And these are some example applications that are very much bottlenecked by data. These are actually forming the core of a lot of our infrastructure in many, many workloads like machine learning. And data is a big performance and energy bottleneck in them. These are some of the other applications that we use right now, actually. Many of you may be using browsers today. Right now, we are definitely using Google's video playback and capture engines with Google Meet today. And certainly machine learning frameworks are in play while we're using them. So we're actually exercising all of these workloads today, right now. And data is a huge performance and energy bottleneck in them also. I'm going to give you some examples. And this is an example from genomics. Basically, in genome analysis, the sequencing machines that we have been designing so far are very powerful. Basically, we can generate a lot of genomic data today, and we can generate it at much lower costs than we can actually generate transistors. You can see that genomic data analysis cost is, generation cost is reducing much faster than Moore's law is reducing the cost of transistors. As a result, we have a lot of genomic data that we cannot deal with. We cannot analyze this data fast enough. So we have a huge computational bottleneck ahead of us in terms of doing scientific discoveries, in terms of creating new machines that can be useful for our health and medical purposes, and in terms of dealing with pandemics, for example. And I think this is a very special interest of mine. We do a lot of work in bioinformatics, for example, in machines that look like this. These machines are great in generating data, but they're actually quite bad in processing data. They're actually extremely inefficient because they cannot do any processing on the device. You have to move the data to a data center, or at least to a nearby computer so that you can process it. And that processing takes a lot of time, and the data movement costs a lot of energy. And we want to change that, basically. So if you're interested in this topic, so basically data is a huge performance and energy bottleneck. And if you're interested in this topic, we actually write a lot of papers. And this is a recent, more accessible overview paper that talks about why do we want to accelerate genome analysis, what kind of medical advancements and potential scientific discoveries it can enable, and what is the state of the art on this topic. And we actually have more specialized accelerators for this purpose also that you can take a look at. But the future, I think, is going to be very interesting. You can see that these devices we already have today, but we don't have intelligence inside these devices. These devices cannot do much by themselves except for generating data. And I give some lectures on this topic. If you're interested, you can certainly look at the lectures that Professor Dinçer mentioned, for example, online and on our site. And feel free to contact me if you have any feedback. But this is just one example. Basically, machine learning is another example. I didn't want to use that since machine learning everybody knows about, but genome analysis is an up-and-coming workload that's going to be a lot more important into the future. But in these workloads, data overwhelms our machines. It overwhelms the storage capability, communication capability, as well as the computation capability. And data greatly impacts robustness, energy, performance, cost, and trustworthiness, as I will discuss. If you look at the fundamentals of a computing system, it consists of computation, communication, and storage and memory. And so far, we have heavily optimized the computing unit a lot. We're very processor-centric because if you want to process the data has to move from the memory and storage unit to the communication unit and then to the computing unit. And we cannot process the data anywhere else. And that's the processor-centric paradigm that we've been used to so far. And I will argue that that's not going to be energy efficient and also potentially trustworthy going into the future. So we need to rethink the system. So if you look at processor-centric systems today, they look more or less like this. This is my cartoonish picture from about 13, 14 years ago that I drew when writing an NSF proposal in the United States. But basically, if you look at a system today, computation is a very little part of it. Only the red parts, the cores, are doing computation. You can think of accelerators as well. Everything else is dedicated to data storage and movement. Caches, interconnects, other caches, other interconnect, controllers, other interconnect, main memory, other interconnect, storage devices, other interconnect, etc. Most of the system, more than 90% of a single node, is dedicated to storing and moving data. Yet, we're still bottlenecked by memory. Yet, basically, data still overwhelms modern machines. So in these workloads that we're exercising right now, we did a study together with Google a few years ago, and we basically showed that on modern workloads, modern data sets, more than 60% of the entire system energy of these workloads is spent on moving data across the memory hierarchy. We're going to get back to this paper, and we're going to try to fix this problem, basically. And that's a lot of energy inefficiency. So my axiom going forward in this talk will be that an intelligent architecture handles data well. We want intelligent architectures. These are going to be intelligent enough to make decisions for us for every aspect of our lives. Why don't we actually make them also more intelligent so that they can actually become better over time? Of course, this brings the question of what does it mean to handle data well? And I think there are three components to this. First, I believe we should ensure that data does not overwhelm the components of the system we design via intelligent algorithms, via intelligent architectures, and more importantly, via whole system designs, all the way from algorithms, architectures, to devices across the entire computing stack. And I think this is fascinating. I'm going to talk a lot about this in this talk. We should also design our systems so that they can learn over time based on information and data that's flowing through the system. Because there's a lot of data that flows through the system. And today's systems are not good at taking advantage of this data and metadata. For example, I'm interacting with my cell phone for more than 6 years. And this cell phone has not learned anything in its hardware in terms of what I have done, in terms of what applications have executed on it. And it doesn't customize its policies. It's not self-optimizing. It's from the perspective of a human, for example, whenever we see something, we are reinforcement learning agents, and we're also other types of learning agents. And we interact with the environment, and we actually improve our decisions. We become better. We're learners, basically. But these systems are not learners. They're designed by humans, and humans have made some decisions in their designs, and they're still doing exactly the same decisions, taking exactly the same actions, regardless of whatever environmental conditions are, whatever users are, whatever workloads have been executing. So I think this is bringing us to the self-optimizing systems, self-learning systems, and we're actually falling a lot short in this one. I'm not going to talk about this as much since we do not have a lot of time, but I think this is going to be extremely important going into the future as well. And finally, we want to design systems that can understand and exploit properties of different data. Today, we actually have a lot of different types of data. Data has different types of properties, different energy properties, different privacy properties, different security properties, different compressibility properties, different error tolerance properties, approximability properties. You can actually come up with many, many different performance and criticality properties. But this information doesn't get even discovered or communicated to the underlying algorithms, architectures, and systems. And the underlying system cannot take advantage of it because no communication occurs, basically. I think we need to change that. We should communicate properties of different data so that we can optimize our decisions in the software as well as hardware architectures underneath. So this brings us to the corollaries, basically. If these three are important, we should really design architectures that are more data-centric as opposed to processor-centric, so that we don't move the data all around. And I'm going to spend most of the time on these data-centric architectures today. If we have time, probably we won't. I will also talk about designing systems that are much more data-driven as opposed to human-driven decisions. These are self-optimizing systems that basically improve their decision-making based on the data that they see in the field. And this data may be coming from many, many places: workloads, users, environmental conditions, etc. And finally, we would also, probably I'm not going to also be able to talk about this, but we would like to have data-aware systems that understand the different properties of different data and make data-aware decisions as opposed to optimizing themselves for the components that they're dealing with. So going forward, I think the architectures need to be data-centric and data-driven and data-aware. And these also have synergies with each other. So if you want to have a data-centric architecture, being data-driven and data-aware at the same time will make things much, much better and much stronger. Okay, so I believe this will lead us to fundamentally better architectures. But to be able to do this going forward, we really need to revisit the entire computing stack, because we need to revisit how we design the algorithms, how we design the system software, interfaces, logic, and maybe even devices. At least we need to co-optimize the algorithms and the devices. This may sound like a difficult task. And I believe it's difficult. We're not going to do it overnight, but we can get there step by step by taking small steps in the end. But we should really change our mindset so that we can actually take those steps and make them real. Okay, so as I mentioned, I'm going to focus on the data-centric, memory-centric architecture perspective. Even if you look at this perspective, I think there are multiple properties that we want from a system that provides data centricity, let's say. And I think I've listed 4 of these properties over here. If you come up with other properties, please let me know. And the first property, which we're going to focus on most, is processing data where it resides. Basically, if data movement is taking a lot of effort, energy, and performance, we should not move data much. We should really have the capability and the ability to process data near and in memory structures. And also, we should have low latency and low energy data access, because data is the most important commodity that we have. We should have low-cost data storage and processing capabilities. And we should also intelligently manage the data. We should have intelligent controllers handling robustness, security, cost, trustworthiness, etc. I'm not going to talk about a lot of these 3, but I will mention intelligent data management quite a bit, motivating it from a security perspective so that it can lead us also to processing data where it resides. Okay, so let's start with this one. So I call this processing data where it makes sense. Today, we don't have any option other than processing data in the processor or the accelerators. So we have to move the data to a memory, storage, communication unit through processors. We should really enable options so that we can process data in places where data resides and where data moves. And that's what this means, processing data where it makes sense. And this is really an old idea, actually. This is one of the earliest papers written on the topic by Harold Stone, who did this research while he was at Stanford. And this is a beautiful paper that argues for putting logic inside the memory. So this is even though it's an old idea, it hasn't happened for the course of 50 years, but something is changing today. And hopefully I will give you the perspective of modern perspective in terms of in-memory computation. So what has changed? Essentially, we have a huge push from technology today, meaning that technology scaling has become very difficult. As a result, memory technologies that we have, DRAM, dynamic random access memory in particular, is not scaling very well. As a result, we're having a lot of reliability, security, performance, and energy issues. And industry is also open to new memory architectures. Controllers are close to DRAM, and these are some examples that I will mention. I'm going to actually mention even more developments from 2019 and 2021, very recent, where people are actually pushing in-memory computation, even in industry today. And I'm also going to motivate it from the systems perspective, but let's start from this technology scaling perspective, because I think this technology scaling perspective combines a lot of interesting issues like security, energy, reliability, performance, key metrics that we want to improve our systems, and technology scaling is not helping us as much. And these scaling issues are real. This is actually a paper that we wrote some time ago, before we had a lot of evidence into the scaling issues. I'm going to give you some concrete, real evidence in terms of the security problems. But this is one evidence, for example. We did this study together with Facebook some number of years ago, and we basically analyzed all of the memory errors that they have in their system, and we wanted to correlate the memory errors to the failure rate that we have due to memory errors with the density of the memory chips that are employed. So if you look at this picture depicts the chip density on the x-axis and the server failure rate on the y-axis. And as chip becomes denser, that means that cells are smaller and cells are closer to each other. That's essentially technology scaling, technology node scaling. As a result, there's a lot more noise effects that you see in the system. As a result, servers are failing more often, you can see, if they employ chips that are denser. This is data that's while the data centers are operational. And this is actually data from all of Facebook's data centers. It's a lot of data, a lot of memory errors, a lot of memories, and a lot of systems. So it's a very strong correlation. Basically, because of the quadratic increase in capacity and cells are becoming much more noisier, we're having a lot more reliability issues in our systems. And if you're interested, there's a lot more data in this paper that we wrote. We also wanted to really truly understand the underlying causes of these issues. So we built these FPGA-based infrastructures, configurable computing-based infrastructures, where we can actually plug DRAM main memory into them, and actually we can test these memories. And we actually did a lot of studies. I'm going to mention some of these studies over here. This is another infrastructure that we built. This is a more recent infrastructure. We actually open source this infrastructure. People are using it in industry and academia, and we're happy to support it. And I'm going to give you some results based on some of these infrastructures soon. So while we were looking at these technology scaling issues, trying to understand why are there so many reliability issues, we also, together with the Intel, found out that you can actually induce errors predictably in most memory chips that you can buy today. DRAM is the main memory technology that's prevalent in all of our lives. Actually, most of the computers that we design today have main memory as DRAM, dynamic random access memory. And basically, we can predictably induce errors in them. This should really not happen. This should not happen in any technology, processing or memory, it doesn't matter, or communication. we should not be able to induce errors because this could lead to reliability problems. And worse, this could lead to security problems, as I will discuss. So basically, this is known as RowHammer right now. You can predictably induce bit flips in commodity DRAM chips. What was 1 before may become 0, and what was 0 before may become 1. And we found out that more than 80% of the tested DRAM chips are vulnerable. And this is really the first example of how a simple hardware failure mechanism, circuit level, device level failure mechanism, can create a widespread system security vulnerability. As a result, people are writing articles that sound like this. This is, of course, a press article, let's say. They say basically, forget software. Now hackers are exploiting physics. And I like this because this is really getting it to the core of RowHammer. So let's take a look at why that is. Basically, cells are too close to each other. Main memory cells that store data are too close to each other. If you look at main memory, it consists of rows. And if you want to access one row, let's say one cell, you need to apply high voltage to the word line that contains the entire row. Now, if you want to access something else, you need to apply low voltage. In DRAM, this is called activation and precharge. And if you keep doing this repeatedly, activate, precharge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, it turns out adjacent, vulnerable cells in physically adjacent rows get flipped. Some of them, not all of them, of course. Some of them are much more vulnerable to this error mechanism. But this should not happen, clearly. Why should it not happen? Because we're not even writing to memory. Even if we're writing to memory, some things that we're not writing should not change. We're kind of reading from memory, but we're not even fully reading from memory either here. And you can do this in real systems today, basically, as I will show you. Basically, we call this the hammered row, we call this the victim row, and we show that more than 80% of the DRAM modules that we examined from the 3 major manufacturers, there are only 3 major DRAM manufacturers in the world, are vulnerable to this effect. And this is a technology scaling problem because chips that were manufactured before 2010 were not vulnerable to this problem. Basically, you couldn't do enough activations to lead to this bit flips. But all of the chips that were manufactured between 2012 and 2013 are vulnerable to this problem. And going forward, actually, they're all vulnerable, as I will show you more recent data soon. But basically, what's happening? Underlying this is electromagnetic coupling. If you actually are activating one word line with high voltage, you're actually disturbing adjacent cells because you're actually causing electromagnetic coupling in the word lines as well as cells, as well as the bit lines. As a result, you're basically leaking charge from adjacent cells that you're not even touching. Meaning, if you do this enough times, if you do this activation enough times, some vulnerable cells will lose charge little by little, and those charge leakage accumulates, and in the end, you lose the data that are inside these cells. And today, we can actually do these charge loss, exercise these charge loss mechanisms with only, let's say, 10,000 activations. I'll show you real numbers, which anyone can easily do if you know what you're doing. And when we actually wrote the paper that introduced this problem, we said basically this should not happen. Memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And I think this is very fundamental. We said that someone can hijack your computer, and many security attacks are possible. And Google folks, Google Project Zero folks basically showed essentially that. They basically showed that they can take over at a user level someone's computer easily by taking advantage of this RowHammer effect, because these are bit flips, and if you can exploit these bit flips reliably, you can basically circumvent all of the permission checking mechanisms that we built into our systems through software stack as well as the hardware stack. I'm not going to go into details of it. There's a lot of very exciting and interesting literature on it. I'm going to flash some pictures of some of the literature that I'm aware of, and I'm going to actually refer you to some of the papers that we have written. These folks, for example, show that they can gain unrestricted access to systems of website visitors by inducing these RowHammer bit flips through JavaScript. These folks show that they can deterministically take over an Android cell phone, again, by taking advantage of the RowHammer bit flips and fooling the operating system. More recently, these folks, these 2 papers in particular, and there are some other papers also coming up, they show that even though a deep neural network, essentially a very good machine learning program, can be extremely good, very highly accurate, let's say more than 90% accuracy, with RowHammer bit flips carefully introduced, not so hard to do, according to them also, not just us. Basically, they showed that your accuracy can reduce to 10%, meaning a neural network that was making good decisions before can actually start making extremely bad decisions if these RowHammer bit flips occur, either naturally somehow, or if someone targets your system and they attack the system. So basically, we have a huge problem in terms of trustworthiness of our systems. In the future, we're going to rely on, for example, these neural networks in our self-driving cars, medical decisions, and who knows what else, and scientific discoveries also. And if these neural networks are not secure, are not trustworthy, we're going to have huge problems in terms of security, safety, reliability, and progress going into the future. So I think we need to solve this type of trustworthiness and security issues. And this is, if you're interested, we have introduced this problem in this paper. And we were invited to write this retrospective more recently. This covers a lot of the issues related to RowHammer, spanning the entire stack of computing. But this is not state of the art anymore because there was more research that was done recently that I'm going to talk about. But to solve this issue, we really want intelligent controllers. If you have an intelligent controller, avoid these patterns that lead to RowHammer bit flips. And we're actually working on solutions as well. I'm not going to talk as much about the solutions, but I'm going to use this sort of technology scaling issues as a motivator for putting more intelligence into the memory system, such that memory system can detect this sort of attacks and actually prevent them even before they happen. And I think this is a very good direction going into the future. And because the problem is becoming worse, basically, according to our recent papers, newer DRAM chips are much more vulnerable to this sort of technology scaling problems, RowHammer in particular, and existing mitigation mechanisms are not effective. But basically, the problem is becoming much, much worse. And unfortunately, we have a trust problem in the industry as well. So after our paper, industry actually shook up a little bit, and they actually tried to fix the problem, but their approach was not fully good, meaning DRAM manufacturers said, we fixed the RowHammer problem, trust us, we have solutions. And of course, they didn't describe what those solutions are openly. So this was a good opportunity for people in the research community to test those solutions. And we found out that those solutions are not secure as advertised. Basically, we were able to reverse engineer these solutions just enough. And we were able to show that we can actually circumvent the RowHammer solutions that are put into place. And I think going forward, we need to do much better in terms of the trustworthiness and security of our systems. We really need to have more open approaches to security because no component can actually be vulnerable if we want to build a fully trustworthy system that are going to make decisions for us. Again, I'm going to refer you to some papers, and there are solution papers that we're also writing, which you might be interested in. And we actually have a bunch of lectures on this topics if you're interested in this. So hopefully this gives you an overview of the technology scaling problems that we're having. And I think computing is the most important infrastructure that we have today. This is a bridge, right? What happened to this bridge in 1940 was this. Basically, it got a bit flip, and this clearly causes security, safety, reliability problems. It's a famous bridge, Tacoma Narrows Bridge. And it's important, clearly. Bridges are extremely important infrastructure, but I will argue that they're not that important compared to computing devices. Computing devices are everywhere, and they're billions and billions, and they're going to make decisions for us. Bridges are static infrastructure. They're not going to make decisions for us. So reliability, security, and safety problems, trustworthiness problems in computing is going to be much more important. So we need to take it even more seriously than the security, reliability, and safety problems in bridges. And bridges can be fatal. Bit flips in bridges can be fatal. And I will argue that that's true for computing, and even more so for computing. So I think going forward, we will need to take a broad approach to security and think about security as preventing unforeseen consequences. And think about this sort of systems. For example, can we trust our systems just like Mr. Bean trusts his self-driving car over here? I think we have a huge challenge and opportunity for the future, fundamentally secure, reliable, and safe computing architectures. And to be able to do that, we need to predict and prevent such safety, security, reliability issues. And I think to be able to do that, we really need intelligence inside our memory systems, as well as computing devices. And I think intelligent memory, as we have shown in past works, in-field patchability can avoid many failures like this. Again, I'm not going to talk about the exact solutions, but you can find that in literature. So that was an introduction to why we need intelligence in the memory system from a technology perspective. There are other technology issues like retention failures, readers, programming errors, etc. I'm not going to bore you with those. You can read the papers for more detail. But technology is pushing us to do something different in our memory systems today, become more intelligent. Let's take a look at the systems and applications perspective. Systems and applications at the same time are pulling us to do something different because we have a huge data access bottleneck today. Energy consumption is a key limiter, and data movement energy dominates computation energy. In my opinion, going into the future, do we want a world that looks like this, sustainable, energy efficient, breathable, beautiful? Or do we want a world that looks like this, where we cannot even survive? I think we would like energy efficient, sustainability, as well as high performance so that we can solve all kinds of problems we have into the future. So if you look at the problem in the way we design computing systems today, even though data access is the major and performance energy bottleneck, our current design principles cause great energy waste and great performance loss at the same time. Basically, we're moving data all around. Computation and memory are far away from each other. And as a result, we have performance loss. But to overcome this performance loss, we design our systems to become much more complex. We add a lot of techniques in hardware and software to basically try to overcome the performance loss. It's for example, multi-threading, out-of-order execution, many levels of cache hierarchies, and also heavy levels of prefetching. And these techniques actually sometimes work, sometimes they do not work. In existing workloads, many times they do not work because we have a lot of random access in our current workload. So on top of the energy waste that we have because of the data movement, we cause even more energy waste because our systems are more complex right now. So basically, we're in a vicious cycle right now. We have energy waste and performance loss. We're trying to combat it with even more energy waste. And as a result, energy waste is increasing in computing today. I think we need to put a stop to this energy waste. And any kind of vicious cycle can be broken by understanding what the underlying fundamental problem is. And I think the fundamental problem today in computing's energy problem, let's say, is processing of data is performed far away from the data. This is true at the micro scale as well as macro scale. For example, in the macro scale, we're moving data from our devices to the data centers, and that's causing a lot of churn in the entire world. Devices are not capable of processing data. And at the micro scale, which I will talk about, is we have computing and memory, and computing and memory are very much decoupled from each other. As a result, we're moving data within our systems as well. And I think we need to target the problem both at the micro scale as well as the macro scale. Now, we're back to this picture that I showed you earlier. Basically, today's computing systems are overwhelmingly processor-centric. Over decades and decades, we've optimized the computing unit, but we have not put as much attention into the communication and storage units. And I think it's time to change that. And we know that this is a problem, actually. This is an old paper that was written by Dick Seitz. Dick Seitz was the chief architect of the alpha processors in 1990s. Alpha processors were the fastest of their times at the time. And after he and his team designed the fastest alpha processor in 1996, as you can see over here, he wrote this one-page article where he basically said, we designed the fastest processor. It's capable of finishing 4 instructions every single clock cycle. But unfortunately, on this important database workload that we designed it for, it's finishing only 1 instruction every 5 cycles or so. Basically, it's operating at 1/20th or 5% of its efficiency. So why? It's waiting for data to come back. And he finishes the article saying that I expect over the coming decade, memory subsystem design will be the only emphasis from him, important design issue for microprocessors. And I agree with this. And there's been a lot of other studies. This is data from my own PhD thesis, for example, where we worked with Intel together. We analyzed all of the workloads that they were using to design their machines at the time. And we found out essentially the same thing. Important workloads are waiting for data to come back from memory, but the processor is not doing much processing or efficient processing, let's say. And there's more recent data from Google. This is Google's workload, including, essentially, according to them, all of their data center workloads. This includes a lot of machine learning workloads, for example, but you can see search, video, indexing, Gmail, etc. All of the workloads that you may be using, for example. And they basically show that the state-of-the-art processor that they use in their data centers are most of the time waiting for memory. Only 10 to 20% of the time, it's doing processing. And this is because data movement is a huge bottleneck. This is a state-of-the-art processor. It's designed for high performance. Even then, and it actually has a lot of mechanisms to overcome the downsides of memory, but it's still waiting for memory. And you can see more detail in their paper that I would recommend you take a look. And this is because we have a processor-centric design. We have a grossly imbalanced system. Processing is done only in one place. Everything else just stores and moves data. As a result, data moves a lot. And even though we make the processor overly complex and bloated, in the end, these mechanisms sometimes work, sometimes they do not work at all. As a result, we have a huge energy inefficiency, low performance, and complexity problem in our systems. And as a result, even though most of the system is dedicated to storing and moving data, the system is still bottlenecked by memory. Now let's take a look at the energy perspective. These are old data that I borrow from Bill Daly's high-peak presentation. And basically, we're going to compare computation. This is a 64-bit double precision floating point operation, only 20 picojoules in terms of energy. A DRAM read or write, 16 nanojoules, like 800x difference. Basically, a memory access today consumes somewhere between 2 to 3 orders of magnitude the energy of a complex or even simple addition. And these numbers, even though the absolute values have changed, the relative numbers have not changed significantly. The relative numbers depend on the system and which operations exactly you're comparing, but somewhere between 2 to 3 orders of magnitude. Now, the question is, of course, do we really want to move data to the processor to process it if the energy cost of accessing data is much, much more than actually the processing cost? And let me mention one thing over here, because this is really interesting. If you actually took this picture, went back about 70 years ago, when computers were being designed 70 years ago, you would see a different picture. Meaning, at that time, memory access was much more costly than computation, about 2 orders of magnitude. What happened in the course of the last 70 years? Essentially, technology scaling. The technology scaling enabled us to design much more energy efficient and high-performance logic. The transistors became smaller and smaller and much more energy efficient. As a result, computation became cheaper and cheaper. But unfortunately, the memory structures and the interconnects did not scale as well. As a result, even though the computation became cheaper in terms of energy and performance, memory stayed, I'm not going to say almost constant. It also scaled well, but it didn't scale as well. As a result, now we're actually 5 orders of magnitude on the other end, meaning memory is much less energy efficient. As a result, I think we really need to rethink the principles of computing again. The processor-centric design that made sense about 70 years ago, maybe they do not make sense anymore. And I'm going to argue for that. And there are a lot of other papers that you can read. This is the work that I mentioned that we did with Google, where we showed that more than 60% of the total system energy is spent on data movement today in important applications that we're using right now. So I would argue that we do not want to move data in our systems because data movement is the most costly operation that we have. So what do? Essentially, I think we need a paradigm shift to enable computation with minimal data movement, compute where it makes sense, where data resides, enable the ability to actually do the computation everywhere in the system, closer to data. And we want to make computing architectures much more data-centric. Of course, basically, we would like to enable computation capability anywhere in the system, but memory is a very interesting part. I think we should do it in the memory. We should do it in the storage. We should do it in the tape. We should do it in the communication units and the routers. We should do it in the caches, even in the processor chip in the caches. We cannot do processing today. But I think I'm going to talk about main memory today, but the principles that I'm going to talk about are actually applicable to any kind of memory structure going forward. Main memory is interesting today because today we actually have a lot of applications that are designed for main memories, large main memories. For example, we have in-memory databases, in-memory graph processing engines, in-memory machine learning workloads, in-memory media processing engines. We can do that. So what we would like to do is we would like to be able to talk to memory and say, memory, can you do this operation for me? And if you can do it, please do it and return me the results. And the memory, without moving data much, returns the result, as opposed to processor getting to the memory and moving the data many, many times between the processor and memory in the micro scale in this case. But think about this at the macro scale as well. So clearly there are many questions. How do you design the compute-capable memory and controllers, processor chip, in-memory units, software and hardware interfaces, system software compilers and languages, algorithms and theoretical foundations? Clearly, I'm not going to have answers to all of these, and I think we're still working on the answers. But this is an across-the-stack problem. All the way from algorithms to devices, we need to rethink how we do computation. And I think I will mention one thing over here, theoretical foundations. So if many of you have probably taken or taught theory of computation classes. If you look at theory of computation classes, what do we do in terms of analyzing the complexity of algorithms? We count operations for energy as well as performance complexity. But I will argue that we should really, that's a processor-centric paradigm. Going forward, if data movement is the most important thing, and data is the most important commodity in our systems, and processing is cheap or free, we should really rethink how we actually do the analysis of our algorithms and theoretical foundations of computing. Essentially, theoretical foundations of computing need to become more data-centric as well. Okay, so that was a long introduction of why we should be doing processing in memory. Hopefully, I've convinced you from both the technology scaling perspective as well as system and application scaling perspective that we're kind of being squeezed in the middle, and we really want intelligent memories going into the future. Of course, then the question is, what are those intelligent memories like? I'm going to spend the remaining little time on 2 approaches to designing processing in memory systems. These are 2 fundamentally different approaches. One is processing using memory, the other is processing near memory. And I'm going to give you some results. We won't have time to talk about a lot of details, but let me give you the fundamental difference between these 2. Processing using memory is very different from how we design memory systems today. Memory systems today are considered just storage devices, right? They have the ability to store data, but we also argue that they have the ability, fundamental capability, to actually do analog computation on the data as well. So these are memory devices, but they can also be easily repurposed to do computation with minimal changes. So we can use the operational principles of storage and memory devices to actually do computation. This leads to different software challenges that we will briefly talk about. But this is a fundamentally efficient paradigm because you don't move the data that much inside the memory technology. The second one, processing near memory, which we will also talk about, is similar to today's processing paradigm. Memory here, processor here, they're far away today. We're going to put memory closer and closer and closer and closer, such that at some point, memory and processor become coupled, yet we still have a distinct processor from memory. In the most extreme case, memory will be immersed inside the memory, but we're not going to use the analog operational principles of memory to do actually computation. We're going to use a different processor. So we're going to put the processor near memory. And I think this is easier to adopt from a software perspective, but I think it can be equally efficient. And I believe we need to combine both of these approaches to get the most out of minimizing data movement. So let's delve into processing using memory first. And I think I will start simple. I'm going to give you some examples, and I will start simple. I'm going to talk about not even computation. I'm going to talk about data copy and initialization. So data copy and initialization is something we do a lot in our systems today. We copy data, initialize data to 0. And according to Google, it consumes a lot of cycles in their data center. Only 2 function calls. This is amazing, I think. Only 2 function calls occupy 5% of the execution cycles and a lot of the energy in Google's data center. So how do we do data moment today? So if you want to copy this bulk data, the white page, to the gray page today, you have to go through the processor. You have no other option. You have to go through the processor chip byte by byte, do the copy, and write the result back to memory. This is clearly high latency because you do memory accesses many times, high bandwidth utilization on perhaps the most important resource we have in our system, and cache pollution, but you can eliminate that today carefully with some techniques. So you have to go through the cache and pollute them. And unwanted data moment. Maybe we're not going to reuse the data that we're copying anytime soon, or we're initializing anytime soon. Imagine initializing a 1 terabyte database so that you can do machine learning on it. We basically have to go through the memory and actually cause a lot of churn in our system today. So even a small copy, 4 kilobyte page copy, if you don't even go through the cache pollution here, if you actually do it through the memory controller, it takes about 1,000 nanoseconds and 3.6 microjoules. So fundamentally, this is processor-centric. So if you actually question this and ask the question, is this the right way of doing copy if you want to minimize energy, then the answer would be, why don't you just do it in memory without disturbing anything else in the system? And if you do it this way, this is low latency, low bandwidth on most important system resource we have, which is the memory bus, no cache pollution, and no unwanted data moment. So I'm going to show you a result that basically, in the best case, reduces 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. That's between 1 to 2 orders of magnitude improvement in terms of latency and energy. And the idea is very simple. I'm not going to go into the technical details, but if you know how memory works, these are rows essentially that I showed you earlier. They're connected to sense amplifiers called the row buffer. Basically, by doing 2 consecutive activates, you can copy the data from a row to the sense amplifier such that it's sensed, and then the next activate copies the data back into the destination row from the sense amplifier. And you can actually make it work easily with negligible hardware cost. In fact, in some commodity DRAM chips, this actually works reliably as well. Even though the memory chip is not designed for this purpose, you can actually violate some timing parameters in existing memory chips if you design your memory controller yourself to actually make this work. And we have made this work. Others have made this work also. And we see significant performance and energy benefits. Again, I'm not going to go into details, but you can see that the benefits are very significant, more than 1 order of magnitude latency and close to 2 orders of magnitude in terms of memory energy. You can actually optimize these and make them better. Ignore these parts. Basically, we have some solutions to data movement in a general case inside the DRAM chip. But basically, by repurposing the DRAM chip so that we can actually do the data movement efficiently, you can actually be much more energy efficient and high performance. And there are clearly works that are building on it so that you can actually do this more in a more general purpose way. I'm not going to talk about these works, but I would refer you to these papers. But I will talk about the mindset quickly. The mindset is that we're building a lot of accelerators, and they're great for energy efficiency and performance, but they're all bottlenecked by the memory. Why don't we actually have a memory-centric accelerator on the memory side, on the right side of the memory bus, that has actually low latency, high bandwidth, low energy access to memory, and that is specialized to do some computation that the memory is very good at doing. And then we can take advantage of it in our applications, and we can program it similarly to conventional accelerators. And I think this is going to be the mindset of processing in memory going into the future. Increasingly, we're going to find out many, many more functions where we can put inside the memory. And I think we're going to hopefully be successful in this data-centric paradigm. Let me give you some other examples. So maybe I cheated a little bit. I gave you data copy and initialization. But similarly to data copy and initialization, we can actually do simple operations, bulk bitwise operations, and or not and majority at low cost by using the analog computation capability of DRAM. And the key idea is that activating multiple rows performs analog computation due to chart sharing properties of the DRAM technology. And others have shown that you can actually do this with non-volatile memory technologies as well. And you get basically 30 to 60x performance energy improvements on these bitwise operations. And this is functionally complete. You can actually translate any algorithm to bitwise and, or, and not. Of course, this requires some programming effort, but if you go through that effort, you can get significant benefits that I will show you now. And I believe new memory technologies like memristors, phase change memory, STT-MRAM are actually even more powerful because DRAM is fundamentally destructive whenever you do a read. These new memory technologies are fundamentally non-volatile, so you can operate on data with minimal movement. They actually enable more efficient matrix vector multiplication using Kirchhoff's law, so they're actually more energy efficient in matrix vector multiplication, which is very much needed in machine learning applications going into the future. Now, let me give you the key idea very quickly. Imagine that these are 3 rows in memory. I'm showing you only 1 bit from each, But imagine you can do this in millions and millions of bits inside memory concurrently. But basically, we're going to take advantage of the analog operational property. If you actually concurrently activate 3 rows in DRAM, connect them to the bit line, this gives you a majority function, bitwise majority. Basically, due to the charge sharing properties, if at least 2 cells are charged, you get the charge state at the end. If at least 2 cells are discharged, you get the discharge state. And that's bitwise majority, very interesting function. You can actually build many, many applications on top of bitwise majority and not as well. But you can also do AND and OR. We actually have mechanisms to actually do the not as well. As a result, we're functionally complete. And if you actually take a database and actually map it to this infrastructure that can do block bitwise and or not, end to end, you can get significant performance improvements like 12x. This is the query latency improvement of a database. And the improvements actually increase with the data set sizes. And I believe we're just scratching the surface because we didn't really optimize things very heavily over here. I think we can do much better going into the future. And if you're interested, there is more work that we have written. This works introduce the topic. And more recently, we're looking into programmability issues, and SimDRAM framework actually shows that you can actually program this and do much more complicated operations. Similarly, we can actually have security functions in DRAM. I don't have time to talk about these, but you can have physical unclonable functions, as well as in DRAM true random number generators, so that we can build a security infrastructure on the memory side as well. So if you actually want to push intelligence into the memory, we want to have security infrastructure in the memory as well. And this security infrastructure is being developed using the fundamental operational properties of DRAM. Okay, and I think everything that I said about DRAM is actually true for non-volatile memories and emerging memory technologies. So you can actually, by modifying the memory technology slightly, do what I've described in other technologies as well. Now, let me jump into the second approach, which is perhaps easier to adopt. That's processing near memory. And I think processing near memory enables a lot of customization to applications. I'm going to show you some examples from graph processing very quickly. Graph processing is very important in many, many workloads, bioinformatics, machine learning, databases, etc. And this is a workload that is heavily constrained by energy and performance of memory. You have frequent random memory access and a little amount of computation. So we designed a processing in memory engine that takes advantage of 3D stacked memory technologies, where you have a lot of memory stacked in layers on top of a logic layer. And in the logic layer, you can put processing capabilities. And there are even more true 3-dimensional technologies under development that can enable logic and memory stacking arbitrarily with emerging memory technologies. Very quickly, I'm not going to go into details of it because we don't have a lot of time, but I'm going to give you the system design very quickly. The system looks like this, basically. You have this, let's say, cube, memory plus logic. Inside the cube, you have cores, and these cores are very simple cores, and they basically manipulate the data on top of them. And if you want to scale up the system, you basically connect many of these chips together. So this looks like a very primitive GPU. You put your graph, partition your graph on top of it, and whenever you want to update a graph node, you actually move the function to the data. So if we don't move the data around, we just move the computation to the function that operates on the data that's housed in each core. So these cores communicate with each other using remote function calls, and we also have specialized prefetching mechanisms. And we designed systems that can take advantage of this technology, and you can see that they look very different compared to these existing systems. Existing systems always have memory and processor dichotomy, whereas Tesseract memory and processor are closely coupled, tightly coupled, and you get access to 8 terabytes per second bandwidth, as you can see over here. And as a result, you get significant performance improvements in graph processing on 5 important graph processing algorithms. And later works actually improved this. Later works actually improved our mechanisms, and they actually can get closer to 2 orders of magnitude improvements in graph processing algorithms. And energy improvements are commensurate. Again, this is our work from 2015. Later works improve this to almost 2 orders of magnitude again. So you can see that by specializing the system using 3D stack technologies, you can actually get 2 orders of magnitude energy and performance improvements. And I think I will refer you to papers for more. Now, very quickly, again, this is the study that we did with Google. We studied these important workloads that we're exercising right now. As I mentioned, these are very much memory bottlenecked. And basically, we found out that often memory bottleneck comes from very simple functions. And we can design lightweight logic to accelerate these simple functions in memories with using special fixed function accelerators or low power cores. And as a result, we can actually improve the performance of these workloads in a much more programmable manner by more than 2x. And I'm not going to go into details of this, but inference, we do a lot of machine learning analysis. And you can see that machine learning is also very much data movement and data bottleneck. And often the data movement comes from true functions that are easy to offload to the memory side. And again, I will refer you to the paper since we don't have a lot of time. Now, let me give you a very quick overview of other things that are going on in processing in memory, and then we will conclude. So we can do this in GPUs, transparently or not transparently. We can accelerate linked data structures, dependent cache misses, prefetching mechanisms, climate modeling that I did not get a chance to talk about, unfortunately. I'm very passionate about accelerating climate modeling mechanisms energy efficiently, approximate string matching, time series analysis that's used in astronomy and many different scientific works, but we do not have time. But to be able to really do this efficiently, we need to revisit the entire stack in the end. But as I will hopefully shown you, we can get there step by step with little changes. And if you're interested in this more, we have written this review article on processing in memory, and this is almost the state of the art. We're going to keep on updating it, and you can take a look at other papers that we've written also. So this is becoming real. Some companies are actually designing systems that can do processing in memory. This is the UpMem startup that we have been working with. And basically, you can put processing inside the DRAM chip. That's what they've done. These are real chips. We actually analyze these real chips, and you can find our papers that analyze these and a lot of talks as well, that I'm not going to go into right now. But these systems are actually quite effective and efficient. They can outperform the CPUs and GPUs in some workloads very, very efficient. In many workloads, actually, very, very efficiently. As I said, FPGAs are actually a good place for doing this also. And more recently, Samsung has finally, a big company has finally put processing in memory structures so that they can accelerate machine learning in memory chips. So I think industry is finally moving in this direction as well. And you can see their chip over here. And if you're interested, you can see our lectures for more detail. And this is a longer version of the talk that I've delivered at the IEDM meeting in 2020. If you're interested, we have a lot more lectures, and I'm happy to talk about it as well. So basically, I think we have a huge challenge and opportunity for the future. We want fundamentally energy efficient systems, and they have to be data-centric, in my opinion. Hopefully, I convinced you with some data and evidence from the field as well. And we want fundamentally high-performance system, and I believe they have to be data-centric also. And I think fundamentally trustworthy and secure and reliable and safe systems also have to be data-centric. And we need to minimize the data movement problem that we have. Of course, adoption issues are important. I'm not going to talk about these since we're out of time, but I believe to enable the adoption of a new paradigm, we can solve these issues with a change of mindset. And there are many issues, but we can get there step by step. And there are other works that we release, and you can take a look at them. But I'm excited about these new medical platforms that can be enabled by processing near data, processing inside the device, etc. And I will refer you to these papers and talks. So that brings me to almost the end of the talk. We do not have time for self-optimizing computing architectures, data-driven and data-aware architectures, but I'm happy to take any questions, and I will refer you to this tutorial if you want to get a quick introduction to those. I'm going to skip these slides and conclude. I think we're almost out of time, so sorry about that, but hopefully this was interesting. Let me conclude. I think today's architectures are not good at dealing with data. It's time to design principled system architectures to solve the data handling problem. We want to design complete systems to be truly balanced, high performance, energy efficient. That will lead us to truly intelligent systems. And I believe they have to be data-centric, data-driven, and data-aware. And we want to enable computation capability inside and close to memory and memory structures and communication structures as well. And hopefully I've shown you examples that this can lead to orders of magnitude improvements in terms of performance and energy efficiency, and non-quantifiable improvements in terms of security and trustworthiness. This can enable new applications and computing platforms, enable a better understanding of nature, because I think fundamentally nature is data-centric, data-driven, data-aware, and who knows what else. And I think we really need to imitate some of the principles from nature and combine it with some of the principles that we have discovered in the design of computing systems today. But we cannot continue with just the principles that we have discovered so far. I think we can get there step by step, and we need to exploit these good principles. More than anything else, we need open minds, and we need to be data-centric. I will flash these again, and I would like to thank people who have funded this research. There are quite a few of them over here. I would like to thank my group who has enabled this research. This is all the research that's coming from my group, and you can see some faces over here more recently. And you can find all of the papers, talks, and videos and artifacts on these websites. Thank you very much. I appreciate the time. I'm happy to take any questions as long as people are willing to ask questions.
Yeah, thank you, Professor Mutlu. It has been very impressive presentation, and we have learned many things. I believe same thing goes for my colleagues and the graduate students. So everyone, the floor is open for quick questions and comments. Okay, Richard.
Just a quick question. Well, firstly, thank you very much. I think it was fantastic, and I didn't know any of that topic. I think this was excellent. One question though is there any drawbacks to going with this system, and what do we have to kind of, or what plans are in place to mitigate any kind of issues related to that?
Sure, I think that's a great question. That I think brings us to a lot of the adoption issues. Certainly, there are a bunch of drawbacks. Meaning, I think one drawback, for example, is our systems are not really ready for this yet. We have a lot of adoption issues to solve. I'm going to show this slide again. I went over it very quickly. But clearly, applications, software are not ready. Programming interfaces are not fully ready yet. We need some system support for it. There needs to be a security infrastructure built around this, runtime systems, compilation systems, and we need infrastructures to assess benefits as well. So there's some things certainly that are good in terms of energy, performance, etc. But the software and programming aspects, we do not know fully. There are cost aspects, of course. Clearly, with any new technology, whenever you merge computation and memory together, you need to have manufacturing capability to actually make the cost better going into the future. And we do not know some of the questions over here at this point. But the manufacturers are moving toward this direction. So I think people are going to understand these issues much better. And there's certainly some, even though I believe security aspects are going to be improved, we do not fully understand the security aspects of it also, because we need to enable these systems to be attacked, for example, by attackers, so that we can understand the security aspects as well going into the future. So there are a bunch of open questions for sure. But I think with research, we can understand and answer these questions better.
Awesome. Thank you very much.
And I think you had a very good comment and question also, basically, what is being done? I think a lot of research is being done, certainly. And more recently, as I mentioned, in 2021, large manufacturers are also moving toward this direction. I think with real systems, we can accelerate this research much better.
Thank you. Any other questions, comments? Abdulrazak, yes, you go ahead quickly.
Yeah. So first, thank you very much for your nice presentation. It was really rich of information, and specifically for me, I just have a question about, maybe it would maybe it's a question, but
I cannot hear you very well. Sorry.
Sorry.
Abdulrazak, it is fading out.
Do you hear me now? Hello?
It's better now, yes.
All right, sorry. So yeah, so I'd like first to thank you for your nice presentation. I just have a question regarding, you said that when you have the idea of having a processor and then the memory, then the idea is putting a small, let's say, if I understand your point, small computation on in the memory. I was wondering why not having kind of two types of, let's say, processors with different, let's say, hierarchies. So one is more dealing with as a normal processor, dealing with the memory directly, and the other one as a master computer, which is dealing with more the software and everything, but kind of connect with this secondary processor. And my second point is regarding the embedded system implementation. Do you think that this idea still holds also for embedded systems with low variable power in memory?
Okay, let me tackle the first one first. So I think we're not advocating, for example, to do computation only inside the memory. I think this picture basically holds going into the future, meaning we're going to certainly have accelerators that are very efficient at the computation that they do. But for the tasks that are heavily oriented on data movement and data, I think we need to enable the capability of computation over here. So I think the future is very heterogeneous. As you mentioned, there could be processors that are customized for different processing purposes, and it may make sense to actually execute compute-intensive tasks to their specialized cores over here. But it also makes sense to execute some of the computations in the memory, and the key becomes scheduling those computations on top of the different accelerators that we have in the system. So I think the future is not just data-centric, but data-centric principles have been lacking in the systems that we design. The future is process-centric as well as data-centric, and figuring out which one we should employ at what points in time for what computation. Okay, so going to the second question, embedded devices. I think embedded devices are actually a great place to actually employ this. For example, the genome analysis devices, today they do not have any computation capability, and actually the memory is a big bottleneck in them, and moving data inside them is a huge energy bottleneck. Embedded devices are usually even more energy constrained than let's say, more general purpose platforms like laptops and data centers today, even though data centers are quite power constrained. Embedded devices, IoT devices, for example, are going to be even more energy constrained. And I think a huge benefit of processing near and inside memory is the reduction of the energy and enabling those computing platforms to embedded device platforms to actually do computation. And I think in embedded devices, there's one more aspect that I should mention, processing near sensors. So today we have sensors, and sensors are directly coupled inside the devices, but the data needs to move from the sensors to the computation units. For example, again, from the genomics, you have these light sensors, for example, in the high throughput sequencing machines, or nanoscale holes in the high throughput sequencing machines. The data gets sensed, and then it gets stored in storage and memory, and then it gets moved to the processor. I believe that the principles of processing near data, processing near memory, can be applied to the sensors as well. I think we should really be doing in-sensor processing. And a lot of the principles that I mentioned over here can be customized to the sensor devices as well, because fundamentally, they're also some sort of memory device. Not all of them, of course, clearly, but we need to rethink the system design so that we can actually do the computation whenever we capture the data, so that we actually don't move the data all around the system. And I think embedded devices have a lot of potential for this purpose that we may not even think about in data centers, for example, or our laptops, because embedded devices are, many embedded devices are actually sensor devices today.
Yeah.
Thank you. And I have one maybe last question, Professor Mutlu. There is a debate actually about human-driven decisions versus data or machine-driven decisions. And some people are raising really big concerns about ethical issues, you know, especially coming down to data or machine-driven decision. So what's your take on this?
I think that's a great question. I think I mean, certainly I think I don't know the answer to this, but certainly it's absolutely true that if the data-driven decisions are biased, if they carry the biases inside the data, if they cannot adapt, for example, then I think we will have problems. And if they optimize for the wrong metrics, for example, then certainly we will have problems. I think we need to be very careful about that in our system designs. And my feeling is, I mean, there are multiple aspects to this, of course, right? For example, neural networks are quite, let's say, prone to this sort of biases, because what they do is they build a model out of the data, and they try to make sense of the data, and they basically summarize the data into this model, and they cannot adjust if they haven't seen the data, right? Maybe we should really be thinking what kind of machine learning models we use in these decisions. I believe not all machine learning models are as vulnerable to bias as deep neural networks. For example, we do a lot of reinforcement learning mechanisms. Reinforcement learning interacts with the environment, and the agent basically learns to make better decisions over interactions with the environment. If humans are, for example, part of the environment, and if actually humans can feed feedback to a reinforcement learning agent that's inside the machine, perhaps we can overcome some of the biases as well with more inputs provided into the reinforcement learning agent. So I see that machine learning models also need to improve, but I see that some of the machine learning models may be adjusted so that it doesn't take just the data, but also the potential for biases as well as the human input in the field into account to improve. Again, I don't know exactly how to do this. My specialty is also not algorithms of machine learning, but I see the potential where we can actually get to a better trade-off between just machine making decisions and just human making decisions, where we can make collaborative decisions so that we can actually make better decisions than both humans and data with less bias, let's say.
I think so. That would be really the optimum, probably the optimum solution.